All right, so we want to start our examples for 2 and 3-dimensional motion. And we have our first one here. Now, I didn't make a separate video on the concept of relative motion because I feel like that's a concept best explained. Not only is that we have a little bit of a gut intuition about relative motion already, but I think that concept's best explained from a physical standpoint through an example problem. So that's going to be our first example problem here. So we wish to row straight across a 63-meter wide river. You can row at a steady 1.3 meters per second relative to the water, and the river flows at 0.57 meters per second. A, what direction should you head? And B, how long will it take you to cross the river? So, first things first, let's get just an idea of what we're looking at. So we can draw just a rough sketch of a river right here and right here, and the river is flowing. So this is our river, and it says that the river is 63 meters across. So the vertical distance across the river is going to be 63 meters. 63 meters. Now, we can pick which direction we want the river to be flowing. It doesn't really matter as long as we keep our signs plus or minus consistent. So I'm going to choose the river to be flowing in this direction. So this is the direction that the water is flowing. Now, it says you can row at a steady 1.3 meters per second relative to the water, and then it gives us the rate at which the water is flowing, 0.57 meters per second. So what we're interested in is the velocity of our boat. So if we have some little boat here, maybe this is our boat, and we're starting right here, we want to know our velocity vector. Not only do we need to know the magnitudes, but we need to know the magnitudes so that we can calculate the direction. If we were to just sit our boat in the river, we would just slowly flow along with the current. But likewise, if we were to only paddle straight forward and we had no velocity in the x direction, we would go forward, but the current of the river would push us along with it. But we don't want that. We want to just flow straight ahead. So we're going to have to flow a little bit against the current and then direct the rest of our motion forward so we stay in a straight line across the river. And so this is where our relative motion problem comes in. So we want to know about that velocity vector. And so this is how I'm going to write this. We want to know about the velocity vector of the boat relative to the ground. Velocity vector of the boat relative to the ground. What is that going to be? Well, we just said if our boat sat still, if we just got in the boat in the water and did nothing, that the river would push us forward, and that would give us some velocity relative to the ground. So for starters, it's going to be the velocity of the river relative to the ground. But then we're paddling as we're sitting on the river. So the river and your boat are moving at the same speed, and then you start to paddle. And that's going to affect your direction as well. So we have to add the velocity vector of the boat relative to the river. And this is our relative velocity problem. Now, these are vectors, and we can think of this as 2-dimensional motion. So we can split this up into its components. We have an x component, and we have a y component. So our x component here, we can just rewrite, and I'm not going to add a third subscript here, so I'm just going to label this one x. So it's going to be the velocity of the boat relative to the ground in the x direction is the velocity of the river relative to the ground in the x direction plus the velocity of the boat relative to the river in the x direction. Now, we don't want to move at all. We don't want to move horizontally relative to the ground because it says we want to row straight across the river. We don't want to move horizontally at all. So our horizontal velocity, of our boat with respect to the ground should be 0. We don't want to be moving left or right at all. Now, this equals the velocity of the river with respect to the ground we were given as well. It says the river flows at 0.57 meters per second, and we've said that the river, we've chosen this leftward direction, So this is going to be negative 0.57 meters per second. And then plus the velocity, v, plus the velocity of the boat relative to the river. And we can just solve for that. So we add 0.57 to either side, and we get that the velocity of the boat relative to the river in the x direction should be 0.57 meters per second, which makes sense. If we were to do nothing, we would go to the left at 0.57 meters per second, but we don't want to go left or right, so we need to even that out so our net motion in the x direction is 0. So this is our x component here. And we could take a look at the y component part just to see. So let's do that in yellow. So in the y direction, we have the same idea. Velocity of the boat relative to the ground is the velocity of the river relative to the ground plus the velocity of the boat relative to the river. So we can look at this, see if we can get any extra information. So velocity of the boat relative to the ground in the x direction, we don't know. We haven't been given anything that we can just directly see how fast we're moving in the vertical direction. Now the velocity of the river relative to the ground, the river is just flowing left or right to left. It's flowing leftward. It's not moving up and down. So the vertical component of the river with respect to the ground is 0. And then the velocity of the boat relative to the river, we haven't been given that either. So it looks like this equation doesn't give us any values, but it tells us something that our gut kind of already told us. The velocity of the boat relative to the ground should be equal to the velocity of the boat relative to the river. And that's because the river is not moving relative to the ground at all. So we have to have some other piece of information that will give us this information that we were looking for, at least. So we look back at the problem, and we have this piece that we haven't used. We can row at 1.3 meters per second relative to the water. So that's a magnitude. So we have the x component relative to the water, and we have the magnitude relative to the water. We're only missing the y component relative to the water, velocity of the boat relative to the water. And we can relate those three things with the magnitude equation. We know that the magnitude of the velocity, and this is we're looking at the boat relative to the river, that has to be the x component squared plus the y component squared, all underneath the square root. That's the magnitude of any vector. So our x component was right here. It was 0.57 meters per second. So we have 0.57 squared plus, and we don't know what this other one is, so it's just the y component of the velocity of the boat relative to the river, and this is the y component, and all of this is underneath the square root. Ooh, yikes. Underneath the square root. Oh, and I forgot my square. This has to be squared here. So we need to solve. We need to insert what we know and solve for this. We know that the velocity, the magnitude is 1.3, the entire magnitude that was given in the problem. And this is going to equal square root, and what is 0.57 squared? That gives us 0.325. So 0.325 plus, I'll just leave it all the same color, velocity of the boat relative to the water squared. But I will continue to make the note that this is in the y direction. Okay, and so now we're going to square both sides. So 1.3 squared equals 0.325 plus velocity of the boat relative to the water squared. And we're going to solve, it's in the y direction, we're going to solve for that piece. And so if I subtract this piece over and then take the square root, I get the velocity of the boat relative to the water in the y direction is the square root of 1.3 squared minus 0.325. And if we type all of that into a calculator, we get about 1.168. So about 1.168 meters per second. So that's our magnitude. in the y direction, but we were asked for the direction. What direction should we head? When you're asked about the direction of a vector, you can always translate that as the angle. We want the angle of the vector. And so we know that the angle that a vector is pointing, we said in a previous video, it was the inverse tangent of the y component of that vector over the x component of that vector. Well, a little divider here. So this means theta is going to be the inverse tangent. Our y component we just solved for down here, that was 1.168. And our x component we know has to be the opposite of the way the river was flowing, and that was 0.57 meters per second. So 0.57. And so if we type that into a calculator, 1.168 divided by 0.57, we get about 63.99 degrees. I'm going to round that, so about 64 degrees. So this is our solution to problem A. Our direction that our boat should point relative to the horizontal is 64 degrees. Now, part B said, how long will it take you to cross the river? Well, we have a bunch of information about the velocities, and we have a certain distance that we're trying to get. So what we're going to use is the horizontal component of our position kinematic. So we want the equation y equals initial position in the y direction plus initial velocity in the y direction times time plus the acceleration in the y direction times t squared over 2. Let me get another little divider here. Okay, so, and in fact, let's go ahead and clear this up with, we'll use a completely different color. So, let's take a look at this. Our initial position, we said we're going to start here at 0 meters. 0 meters, that's going to be our origin, that's going to be our initial position. So this can just go away, that's 0. And this acceleration in the y direction, we're paddling at the constant magnitude 1.3 meters per second. So we're not accelerating at all, so that entire term cancels out as well. And we have the simple equation y equals the initial velocity in the y direction times time. And this is of the boat relative to the river or the boat relative to the ground. Remember we said they were both equivalent right here. Now we want to solve for time. So time is going to be our final position, final vertical position divided by velocity in the y direction. Well, we said that we were trying to get 63 meters across the river. So that's 63 meters. And our velocity in the y direction, well, we solved for earlier. That was right here, that 1.168. So that's 1.168 meters per second. And if we type that into a calculator, 63 divided by 1.168, we get 53.94. So about 53.94 seconds it will take us to cross this river.